introduction.
So yeah, I will briefly introduce you because. So our first talk will be by Antti of NetBSD Face. He has invested a lot of work of porting kernel code into userland, and that's kind of interesting to a lot of people here. So I'm very excited.
Right. Good morning. Is this loud enough? Okay, great. So, as was already stated, I am Antti. I'll be talking about Rump kernels this fine morning. The reason I picked this workshop or this web room was indeed that I hope some of you might find this topic interesting without me having to motivate it very much or spend half an hour on talking about motivation. This will be a fairly introductory talk. I hope it won't be too elementary, but since this is a very small room, if you have questions during my talk, I suggest you ask them right away so I can kind of try to veer on the right technical level of really try not to go into technical details, but you know how it is with people who write too much code. It always doesn't quite work that way. Yeah, so just ask questions and I'll start talking. At some point I'll give a demo if I remember, and we'll hopefully finish at some point too. Yeah, so Rump kernels. I thought I'd start saying what they aren't, but then I decided that would be too difficult, so I just took the wussy approach and actually we'll start by telling what they actually are. So a few Rump kernel cans in case you don't have a general idea yet. So a Rump kernel is a driver container. Now, well, that obviously means it runs drivers, but the word driver is kind of, you know, some people have different ideas of what a driver is. So I take the word driver in pretty much the broadest possible way to mean something which takes some input and produces some output. Well, okay, that's not a very useful definition. But for example, a file system driver is a driver, a system call handler is a driver, network interface card driver is a driver, and so forth and so forth. And Rump kernels are meant precisely only to run drivers. And furthermore, by drivers, they run unmodified NetBSD kernel drivers. Now this, as we'll soon see, has its roots in what the motivation for me originally was and why they had to be unmodified. So I wouldn't start with the NetBSD kernel and port the drivers somewhere and then run them and then maybe port them back. But the idea was that you take the same code and now you can take any version of the NetBSD source stream and run the drivers as Rump kernels. A Rump kernel runs anywhere. Well, that's quite a bold claim. I'm not sure if it runs actually everywhere, but in most sensible environments. So I'm sure we could start coming up with examples of 8-bit microcontrollers and so forth where I'd run into trouble with running Rump kernels. But let's say anywhere which is a kind of environment which could fit something like a driver from NetBSD. You know, they're not 2 kilobytes in size, because NetBSD is quite a big operating system, but I hope the definition of anywhere will become clear during this talk. At least they run in more environments than NetBSD. That's good. Then kind of the how should I say, I assume difference of approach with most people here, which is what I've tried to state by the very cryptic phrase interconnection agnostic. So I assume, and this is an assumption, please throw projectiles at me if it's incorrect, but I assume that when most people create a system, they have an idea of what they want the system to look like, you know, how the requests will be routed, how things are linked together or not linked together, will there be some message passing, or what is the communication mechanism. And after figuring that out, then comes the part that this system should also do something, so then we need drivers. Well, here it's completely opposite. I have drivers, and now I'm thinking, they should actually do something too. Rump kernels are component-oriented, which is again a cryptic phrase, which is just a fancy way of saying that first you build them, you get a set of library-ish components which you then link together. So when I give the demo, you'll see it builds blah 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 blah. Then you know one set links a file system like driver stack, the other one links let's say a networking like file system. Yeah, too early. Networking like driver stack and so forth. Yeah, I won't be showing any demos on actual device drivers today, unless someone really wants to, but that might take a while. Rump kernels integrate fully up to the application level. So earlier I said the system call handler is a driver, so it provides API and ABI equivalent interfaces, so you can run existing binaries against it. But of course it's not limited to running application level binaries. You actually have the complete freedom to plug into it at any point in the stack. So actually the first way I used rump kernels was to write, well, they weren't even called rump kernels back then, was to write file system servers. So instead of attaching to the rump kernel of the system call layer, I did it at the EFS layer. And well, there's no restriction, but obviously they don't do magic either, so you need to possess the correct context before you can call that properly. Okay, so that's a few what you can do with rump kernels. Now, the more important thing, I think, is what you cannot do with them. So you cannot execute programs, which means a rump kernel has no knowledge of, you give it a binary, it's like, what to do with this. So it won't you can't run Firefox with a rump kernel, but you can run Firefox against a rump kernel. So instead of running the process in the rump kernel, you can use it in a library-like fashion. There's absolutely no knowledge of virtual memory, so you either have virtual memory when you run a rump kernel, you don't. There's no knowledge of page protection, no page fault handler, nothing in that area. A rump kernel cannot deal with privileged instructions, which just means it can't. If you try to execute code in a rump kernel, there's a privileged instruction in that code, it will say boom, unless of course you're running in privileged. And then one of the very, very key things is that there's no thread scheduling knowledge, no thread preemption knowledge. Everything is used from the host platform where it runs. And it's completely up to the host how it schedules the threads. and which threads are running. If there's some piggy thread running, it's the host's problem to unschedule that thread. Yeah, so I'm more proud of these cannots than the cans, because this allows a lot of specific targeting, so it allows to solve 90% of problems really well and then completely ignore 10% of the problems instead of solving 100% of the problems in a kind of Okay. One thing, I don't have a timing device here.
I will tell you.
Oh, okay. Great. So how did this type of system come into existence? My original focus, my original motivation was doing kernel development. So I wanted to run the drivers in user space. I was actually writing user space file system servers at the time, and then I found it very boring that we have this different set of Fuse-like interfaces for which it's very nice to write file system drivers, and then we have this kernel-y thing where it's easy to write the file systems. They just end up being different. We can't use them interchangeably, and testing the kernel ones is a real pain. People will tell you, well, you use a virtual machine. Well, no. I don't think virtual machine is any easier than using a real machine, apart from you don't actually have to own 2 copies of the hardware. You still have so much extra pain. I can't tell, or if you can't relate to the concept of being able to debug drivers in user space, it's really hard to explain. It's just so much easier, so much nicer. But of course, due to this motivation, I had to use the unmodified kernel drivers, because a situation where I first take kernel drivers, I port them into user space, of course introduce a lot of bugs in that process, then do my development, then port them back, and then again introduce more and more bugs. Well, it's quite annoying. Plus, if I actually want to track some bugs, what's the probability that they will happen in both environments and so forth. So I started with an unmodified file system driver, got that working. Then, of course, a file system driver depends on a lot of things. You can't just run a file system driver alone. It allocates memory, it does block device access, it does VFS, it does locking and so forth. And then, of course, the next logical step was to think, okay, well, now I have the shim for these other things which the file system driver uses, but what if those change, or what if those have bugs, and what if I would want to develop and debug those, or test them? So eventually, this kind of cycle of supporting more drivers and figuring out what they need somehow converged, and I think this problem was solved some years ago. So this was developing or being able to run NetBSD kernel drivers in user space on NetBSD. So then I started getting questions like, well, okay, so now you have this TCP IP stack running on NetBSD in user space. Could we run it somewhere else too? And then at some point I kind of got tired of writing emails which said, yes, you could, but you would need to do this and this and this and this and this. Because over the time I got through some discussions with people, I got a pretty good idea of what that would require. So eventually I just thought, well, since the kernel development driver problem, at least for me, is now solved, so this system seems generally useful, so why not just target reusable drivers? There seems to be interest for that. And and that's what I did, and that's pretty much why I'm here talking about this today. Now, of course, some of the kind of key criteria for reusable drivers and kernel development is different. Performance, for one. And that hasn't been fully solved, but hopefully I will be able to explain that performance is okay, but there's some things you need to understand so that you can tune things so that they really run without overhead. So if we revisit, in this light, if we revisit the limitations the Rump kernel cannot, we see that they have actually now turned into advantages. So instead of having to start a virtual entity in which you create a process, you can directly call a Rump kernel from anywhere you run it. You don't need virtual memory, which is kind of important if you don't happen to have virtual memory on that platform. You don't need privileged instructions, or there's no use of privileged instructions, which means you don't need privileged mode, you can run it anywhere. And of course the use of host threads, so you can directly control, or you can easily control the scheduling policies. So there's no, added layer of extra confusion. Is it too early? Nobody has any questions? Or am I being too understandable? I can also try to be less understandable. So, just to get into a small amount of technical detail, what makes a Rump kernel tick and talk? What makes it work? There's two different things. First of all, you have to be able to extract just the drivers from the monolithic kernel base. Now, at least according to some mythology, a monolithic kernel is so messy that you couldn't possibly do this. But guess what? It's actually quite easy. But there's a small number of certain kinds of changes you need to make sure that the drivers really are orthogonal to all the other components in the system. And this can be done without any linker types, indirections, or anything like that. So I just use the normal linker, and I'm able to select the set of drivers I want. And I call this kernel architecture the any kernel, which is, it's a bit of a joke. You can really laugh at it, because it kind of says that, okay, in this kernel the drivers you can really monolithic, micro, exo, whatever kernels you want. Yeah, and yeah, of course the any kernel doesn't do magic, so if the file system driver uses the block device actually has to be present. If it allocates memory, it has to have access to those memory allocation interfaces, but kind of. And any kernel is a kernel architecture out of which you can carve these kind of driver stacks. Okay? So that's pretty much what NetBSD is now. And the second thing which makes a Rump kernel work is hypercalls, because at some point it does have to allocate memory, it does have to do I/O access. It would be pretty boring otherwise. But these are very high-level hypercalls, so they're not kind of the hypercalls in the sense you would think with virtual machines. So there's no virtual memory support. So there's nothing like we'll change this page table in this way, or do this or do that. It's yeah. allocate memory is one of them. There's things like simple I/O routines, like display a character on the screen. So I'll talk a bit more about hypercalls in the following slide. I probably wanted to say something more, but I'll say it. So hypercalls you can generally in Rump kernel. Yeah, I wanted to say that the hypercall interface is very small, and I also wanted to say that I actually wanted to put the manual page for the hypercall interface on the slide, and then I have to say I couldn't figure out how to do it. Apparently, I don't know if someone knows how to do multi-column text in OpenOffice. Please come see me after. Yeah, so hypercalls are divided kind of into, or I've started realizing that there are really two sets of hypercalls. There's these things which make the Rump kernel run at all, like for example memory allocation, and also one important one is synchronization, because a Rump kernel uses host threads. So synchronization has to happen, like a mutex lock has to happen via a hypercall, because the Rump kernel cannot do scheduling. So if the lock is taken, then you need to inform the host that, hey, now I can't run this thread, please block it. Yeah, so platform level hypercalls are one, and I/O hypercalls are the other. So just for which platforms do the hypercalls exist? So, well, first of all, I claim any machine architecture is possible, even those which don't run NetBSD. It's fairly trivial. Actually, the only machine-dependent thing is if you have a multiprocessor system, you have to have some knowledge of atomic instructions and memory barriers. But that's the only assembly you would maybe really want to write. Yeah. So here's some examples. So POSIX, which is a funny way of saying user space, and it says and JavaScript, which means JavaScript. So at one point we were discussing JavaScript, and then I thought, well, if Rump kernels run anywhere, it should be possible to compile them into JavaScript and run them in a web browser. So then I did that. And why it's POSIX is because the C to JavaScript compiler that I used happened to nicely emulate a POSIX environment readily, because the C to JavaScript compiler wanted you to be able to take just any user space C program and compile it into JavaScript and run it in a browser. So that's why I consider JavaScript to run on the POSIX hypervisor. Well, but then I thought that POSIX is kind of boring, so let's try it. We can make Rump kernels run in the Linux kernel. Well, that worked too. That was nothing interesting. Then actually, kind of a more interesting thing was because user space and the Linux kernel, they're kind of, high-level systems. They provide a lot of interfaces, etc., etc. So, what if we ran this on a really minimal system? So then I tried how difficult would it be to make it run on the Zen hypervisor, and again, I'm borrowing some parts from MiniOS, the bootstrap routines, etc. I don't like writing Z. It was some days of work. Well, then what actually makes the Zen thing interesting was Justin is still sleeping. Well, Justin, who is still sleeping, contacted me and said, okay, well, now you have this kernel set of interfaces booting directly as a Zen guest. But I would like to run an application, and in case you haven't heard, applications run on top of libc and libraries. So then we started thinking, well, since Rump kernels already pretty much provide the whole set of NetBSD system calls, so what if we just take the NetBSD libc, rip out the trap parts of the hypercalls, push in function calls into Rump kernels, and could we actually run applications directly on top of Zen, on top of Rump kernels? And the answer is yes, so that was also very simple. By the way, everything I'm talking about, there's going to be a link to it on Google, so you can conveniently find it later. I/O hypercalls. I won't go into details, but I/O devices I've started noticing have specific needs. So instead of kind of treating them as platform hypercalls, it's easier to attach them to specific drivers, and that way you gain some more flexibility. Here's just some examples of networking or packet processing facilities available with Rump kernels. Now, this is actually missing PCI drivers for no specific reason, but, well, maybe for that reason, because these drivers are kind of, you have, or all of these facilities provide a very high-level interface to networking. I don't know if you're familiar with UPDK or NetMap or Snap Switch or well, TAP, everyone is probably familiar with. So that kind of interface. And then if you take PCI drivers, the I/O hypercalls happen on a different level. With PCI drivers, the hypercalls are actually mapping the device registers, allocating DMA safe memory, and so forth. The only thing I actually want to, how does this work still? Hack-ish. I'm very proud of that hack. When I did the Linux kernel thing and I wanted to run the NetBSD TCP/IP stack in the Linux kernel, of course I needed an interface in there. So then I started looking at, well, how difficult is it to implement a networking interface in the Linux kernel. Then I concluded, well, dinner is in a few hours, so it's a bit too difficult. So what I just did is, instead of calling the network interfaces of the Linux kernel, I call right at the top of the Linux kernel into the file system interfaces of the TAP device. Works. And it's 5, 7, 10 lines of code. Well, block devices aren't as widely supported, but anyway, these are just examples. Yeah, so I thought I'd do some sort of demo. Let's see if the network works. Is it readable?
Yes, so far.
So far. That sounds like a challenge. What's the correction? This is probably better. Okay, so this is some silly Linux machine. So what happens if I want to build the NetBSD kernel drivers in user space on this one? So I would go to GitHub, get a build script, then I hope that the network works. Yes, and then the terminal is very wonky, but maybe I should make it one smaller. Okay, so now, oops, but this is just a build script, but then I can run it. I will give it 2 parameters. You don't, yeah, so I will give it 2 parameters. You don't necessarily need to give them, but this will just make the build a bit faster and it will produce less output. And it's even working fairly quickly. So I'll just leave that running as a distraction and continue talking. So what's happening is that the script is now fetching the necessary subset of of the NetBSD source code from fetching it from a GitHub mirror. You could theoretically, like I said, use any version of the NetBSD source code, but sometimes this script I do some modifications when it depends on a later version of NetBSD. Sometimes NetBSD doesn't build or you know, these kind of things. So I just eventually I concluded that it's easier to give a recommended source snapshot. This is the development head, I think, from about a month ago. I usually update it maybe monthly or once every 2 months or so. Well, the other reason was that I like the blow away your entire source tree and start from scratch approach to development, so I get all the printers and other silly things out of there, so it's easier for me if I can just run a script which does everything. So what's happening now is building the the necessary tools to build the Rump kernels. There's a few funny tools in the NetBSD build, like the make is non-standard and so forth. So NetBSD itself is able to be cross-compiled on any system, so this just reuses that same functionality and builds the necessary tools, again with the idea being that you could build this pretty much anywhere, you don't run into problems. Of course, it doesn't build the entire subset of tools that NetBSD builds, because the standard NetBSD build, for example, builds a cross-compiler for NetBSD. And now we don't want to build the drivers for NetBSD. By default, they're built for the target, which the host compiler supports. The intention, of course, being that we can run them on host. Okay, so after the tools are built, it goes into actually building the drivers, which, well, it's not very interesting to look at, but they are building. Okay. Yeah, there's now new information. Okay. So this thing is building. I hope it builds quickly because I don't have much time left anymore. And well, it doesn't generally take very long. But you can see that there's a bunch of drivers which are conveniently line wrapped for minimal readability. But you can see there's things like the SCSI mid layer, NFS, soft RAID, random whatever thing, fact file system support, some USB nonsense, I think. USB is all nonsense. I wonder if my laptop was slower overnight. Yeah, but anyway, this demonstration is just to give you the impression that you can really just run a single command and go out for coffee, and this has been kind of my usability, or kind of level of usability I want to. Oh yeah, sorry, you should say.
Is it compiling the whole BSD stack? I mean,
sorry,
the BSD kernel, or is it using just the specific parts?
No, this is not compiling the whole BSD kernel. This is just compiling everything that's necessary to run Rump kernels.
Because I see it compiling like LTS.
Sorry?
I see it's compiling functions like FTS, so I'm wondering why it is using...
How did you see it compiling functions like FTS? You are cheating. Well, yes, because if a driver uses something like FTS, then you have to provide it. I mean, that's the any kernel carving thing, so you need to figure out the set of things you need. Okay, it finishes, it runs a bunch of really simple tests like I mean, there are a lot more tests in NetBSD because NetBSD, or at least some parts of the NetBSD kernel is tested using Rump kernels, but this is just to give some sort of idea that it actually works on this system. And if we go into the tests directory, there's things like well, actually, let's run this other test. This is kind of a thank you. This is kind of a cheating test because it doesn't do any file system access. It just boots a Rump kernel and reads from a kernel file system, but you get kind of the idea of, oops, okay, not like that, or how quick it needs to execute a Rump kernel. So it usually takes around a bit over 10 milliseconds on this hardware. And it's a user space program. You can, for example, let's say you can, there's a artificial construct of CPU for things like RCU to work, which in the sense of Rump kernel just means how many threads can concurrently enter a Rump kernel. And then the interesting case is, of course, setting it to 1, in which case you can optimize all machine-level atomic memory operations away. In which case you can measure 30% performance improvement. I didn't say you can do anything useful. Measure 30%. Does anyone want to see anything else? No? Yes. I still have a few slides left, and these are very important. So, in the talk abstract, I thought I promised to tell some anecdotes, and so I'll tell some anecdotes. So I think this is the main reason why things are why they are now. I was very lazy. I wanted to develop the drivers in user space, but I didn't want to do anything extra. Now, everyone of course knows that you can emulate virtual memory by memory mapping a file and then remapping it, or doing interrupts with signals, or kind of providing a standard user mode operating system. But I was too lazy to do that. And actually now it turns out all this architectural laziness is really, I think, what gives Rump kernels a unique advantage. They run anywhere, they integrate very nicely, they can do run to completion, so all of these things are kind of suddenly being good things. Well, then a second anecdote, I'm not sure if this is more or less important than the previous one, but do not be lazy. And yeah, this might seem contradicting, but I think on an architectural level you should be lazy, but for fixing things, especially for working with the build system, which is the worst thing ever, I mean, working with build systems, you should not be lazy, because every time I'm lazy with something like that, it comes to bite me when I'm preparing a demo or whatever. So fix the build system always, or it bit me what? It usually bites you on Friday evening. Okay, well then, kind of following the Einstein principle, things should be made as simple as possible, but not any simpler than that. I said that the Rump kernel hypercall interface is a very small interface, and I want to keep it a very small and simple interface. But of course, small and simple are not the same thing. So at the expense of making it simple, I want to make it small, so that there are few stupid mistakes there where some calls actually, without getting into details, do more than one thing. And this is, again, something that bites me. So very important not to make things too small. Anecdote, well, coding is really easy. I usually say that anyone can write a TCP/IP stack in a weekend. That's no problem. But then putting it on the internet and having it work, well, that might take a bit more work. So the idea, or kind of, I would very strongly suggest that nobody, for whatever reason, tries to write, develop, debug code which has already been written, developed, and debugged. And a lot of things that I've been doing have really felt like magic at some point, because software developers, I think everyone's used to like write it, then yes, now it compiles, now it will work, and then spend the next week debugging it. But most of my recent experiences have been, okay, I just pull these components together, since they're all tested code, they all come unmodified from NetBSD, real programs run on top of that, so things just, really, seriously, they just tend to work. I think this.
Yeah, but the important part was that they were previously well tested.
Yes, exactly. Because someone has already invested this making it work
But
effort.
if the available modules are not of such high quality,
Well,
it's not better to write them yourself.
Well, yes. Then we get to the first principle. Then one thing which I became a huge fan of throughout the years I've spent working on this is automated testing. I'm under no illusion that I could even be talking here if I hadn't really made a push to automate all testing. It's really critical. Things bit rot if you don't test them every 5 minutes, which is kind of weird. So okay, well, since it's an open source talk, open source talks always need to end in please and the begs of everyone suddenly magically joining this project. But if you're interested, well, really the one thing I would want is try it out, give feedback, say that this would be a useful feature, that would be a useful feature, that's a rubbish feature, don't develop that. So I don't have to figure out what I want to do. Another way to contribute is to just work on NetBSD, improve NetBSD. That will automatically improve the drivers available in Rump kernels. And then there's a few kind of a bit harder, not weekend projects, like improving the performance of the TCP/IP stack. I have a pretty good understanding, I've documented the steps, but it takes a bit more effort and use cases. Or, for example, finishing the ZFS driver. It's kind of almost finished in NetBSD, and I would really love to have it available for distribution with Rump kernels. It's not there yet. So everyone please hack on ZFS on NetBSD. I will be expecting results tomorrow. Okay. Here are some links, URLs, and other pieces of useless information. There's a mailing list, a rather fresh mailing list. If you have any questions which you don't get a chance to ask during my, 55 seconds of Q&A time left, or if you don't run into me here then please ask on the list. Questions? Mm-hmm.
To what degree is the approach specific to that VSD, or is there something that would hinder you from using your approach on some other monolithic server?
Yeah, so the question was, is the kind of ability to take drivers this way specific to NetBSD, or can you use it on some other systems? No, it shouldn't be specific. I've actually done similar ports, similar prototypes for both FreeBSD and Linux, but of course I did only the easy parts. And then I got kind of the impression that it could work. I didn't run into anything where it couldn't work, but of course it's one thing to hack a bit on your private tree and then do something which you can mainline. But no, there shouldn't. I mean, to be honest, there's not really that much of an approach. It's just, this doesn't work, let's fix it. Any other questions? I have 0 minutes left. So. No? Thank you.
Thank you.